Hi there. So if there are any VCs in the audience today, please let me know, because I have a great pitch for you for a new web analytics startup. See, we won't need to bother with tracking cookies or any of the usual nonsense. Instead, we'll just steal people's history directly from their web browsers. And that's what we'll be talking about today: history sniffing attacks, or the trial and error approach to slurping out history data. Modern browser security rests heavily on the idea of using OS-level sandboxing mechanisms to limit the capabilities of untrusted code. What browsers have done here is they've taken web content, that arbitrary code that you just download and run on your system willy-nilly these days as you browse around the web, and they've built this whole fortress of sandboxing around web content to keep it from getting at the rest of your system. This is a pretty robust defense generally, but an attacker doesn't necessarily need to breach this sandbox in order to do harm. Because web content is not the only thing trapped inside that impressive fortress that browsers have built here. They've also just left this perfectly good stack of gold bars in the form of history data, just sitting around unprotected, where malicious content can make off with it without having to traverse any sandbox boundaries at all. Now you probably know that your web browser keeps a history of your travels across the World Wide Web in the form of a set of URLs that you've navigated to. Now, browsers maintain this history log in order to power various bits of functionality. For example, the fact that links turn from blue to purple when their destination URLs have been visited. This is known as the visited links feature, and it has a pretty spotty track record with regard to the privacy on the web. It all started in the bygone era of 2002, when attackers first figured out that they could abuse this visited links feature to get the browser to leak to them the visited status of any given URL for their victim's web browser. All they had to do was pick out a URL they were interested in knowing and plug it in as the destination of a link element. And they would just ask the browser for the color of that link, and if the browser said purple, then they would know that that URL was visited. If the browser said blue, on the other hand, then they would know that the link was unvisited. This is the essence of a history sniffing attack, exploiting some difference in browser behavior which depends on that secret visited bit for a given URL. And as it turns out, if you have one of these attacks, then you can use it to put together a pretty detailed profile of your users. You can see what sites they visited, slurp up their history data for marketing or extortion or other underhanded purposes. What you do is you put together a huge list of all the URLs you think that someone might have visited on the web, say based on the Alexa top sites index. And so you've got this whole big list, and then you just run it through your history sniffer, enumerating your victim's browser history one correctly guessed URL at a time. And the faster you can go through this list, the more history data you can steal from your victim during the time that they spend on your web page. And so we measure how powerful one of these history sniffing attacks is in the form of this bandwidth number, the number of URLs that lets you test in your victim's browser per second. So if this all got started in 2002, then by 2010 we were seeing bandwidth figures on the order of 3,000 URLs per second. And this is what finally, 8 years after the initial disclosure, pushed browser vendors into acting to protect their users, plugging up that original visited links hole, even if it broke backwards compatibility a bit. But of course the story didn't end there. In the intervening years, various new techniques for doing history sniffing have been discovered, mostly exploiting that visited links feature again, but in different ways. Now, browsers have more or less patched up each of these attacks as they come out in a very ad hoc, individual fashion, duct taping over each leak at the surface instead of addressing the root cause, which is the absence of in-depth privacy protections for history data. Now, none of these new history sniffing attacks have really reached that scary 3,000 URLs per second figure again. That is, not until now at least. Because as of our camera-ready paper deadline a couple of weeks ago, our most powerful history sniffing attack, CVE 2018-6137, had hit that 3,000 number again, already making it the fastest we know of since 2010. Now, actually, as of me giving this talk, we've managed to double our attack's bandwidth to 6,000 URLs per second. So, extrapolating logically from there, we should hit like 3 million by Christmas. Now, our paper actually presents not one but 4 new history sniffing attacks, each exploiting a different feature of the modern web platform. And taken together, these 4 attacks target Chrome, Firefox, Edge, Internet Explorer, as well as several security-focused browser designs to be tested and found vulnerable, with the exception of the Tor Browser, which doesn't track history data at all. So today what we're going to do is build up our own history sniffer to run in the victim's web browser. It'll take as input a set of target URLs that we're interested in, and it will, as quickly as possible, try to spit out which ones were visited by our victim. We'll walk through this process step by step, from identifying a web API which we think we can twist into letting us do some history sniffing, all the way through to building it up into a fully fledged, high bandwidth, real-world history sniffing attack. Now, the best place to go hunting for vulnerabilities is in new code. And as it happens, Chrome just dropped in a big hunk of code toward the beginning of this year to implement the CSS Paint API. This is a standardized W3C candidate recommendation, so it's coming to other major browsers soonish. And what it's all about is, well, we as a society, we really love JavaScript. I mean, we must, right? Because we've crammed it into our servers, our speakers, cars, airplanes, medical devices, satellites. They're all running JavaScript now. And so it's been decided that to take this further, we're just going to let web developers directly inject JavaScript right into our browser's rendering internals with the CSS Paint API. But before we get around to recognizing this API, we need to understand how it works. You know, why would a normal human ever use this CSS Paint API? Well, say I love chess. I love chess so much that I run a whole website just dedicated to chess and chess-related topics. And say I've handcrafted this beautiful chessboard PNG image here to use as the background of my chess website. And I can do that by just dropping a line of CSS in my web page, which sets its page's body background to this chessboard.png file. With my browser window at this size, everything looks great. But to my shock and horror, as I size up my browser window, you can see that the scaling the browser has applied here is not great. It's left the edges of all these squares just blurry and warped, which is unconscionable to me as a true chess aficionado. Fortunately though, browsers and vendors have gifted me with the CSS Paint API, with which I can take back control over how my page draws its chessboard images. So I start by whipping up what the CSS Paint API calls a paintlet script. This is a small, self-contained JavaScript program which takes as input some width and height values and draws out a perfectly crisp chessboard image suited for these dimensions. And with that written, I pop back open the source code for my web page and drop in a little JavaScript to tell the browser to download and install my paintlet script into the page. Then with the paintlet installed, I can hop over to that CSS and rewrite it, so that the background image of my page's body will now be painted by that chessboard paintlet script we installed. Now with all this set in place, if I pop open my chess web page, it ends up looking like this. Now let's step through what happens this time when we try resizing our browser window. First off, the browser detects that my page's body element has had its width and height values changed. And whenever a property changes on an element, which affects its visual appearance, then the browser comes along and sets this invalid flag on the element. So then, when the browser renders the next frame of the page to the user screen, the browser loops through all the elements on that page, which is marked with this invalid flag. And it does a repaint on each one. And so to repaint my page's body element here, the browser ends up having to call into the paint callback inside my paintlet script, which goes ahead and draws a brand new chessboard image to match the new width and height. And that gets filled into the web page, and you can see that it's now all nice and fitting with the new size. And then from there, anytime I resize the window, the browser will automatically repeat all these steps for me, automatically coming up with new chessboard images to fit any given size. So on the surface, this CSS Paint API would seem to have little to do with security and privacy, as you can see from the spec. And yet, browsers are such intertwined balls of stuff that it's hard to do anything significant with them in terms of extending them without having to step on security and privacy somehow. In this case, the problem we run into is that visit links feature, which we talked about earlier. See, browsers actually put a lot of time and effort into making the rendering process for link elements as side effect free as possible with respect to which color the browser picks out for the link depending on its visit status. Now, unfortunately, the CSS Paint API kind of undoes all that, because if we take a link and set its background image to be painted by, say, our chessboard paintlet script here, then whenever the value of that secret visit status bit on the link changes, the browser repaints the link and makes an extra column to code we control. So at this point, we can consider the CSS Paint API potentially vulnerable to being used for history sniffing. because in conjunction with visited links, it causes the browser to behave differently based on the value of that secret status, visited status bit for a given URL. Now next up, we'll see if we can build up a basic attack using the CSS Paint API to, for any given URL of our choosing, trick our victim's browser into leaking the secret visited bit that's associated with it into some code that we control. So say my goal as an attacker is to figure out if my victim has visited ashleymadison.com. We're going to walk through these steps that I've performed to carry out this attack. At the same time, the effects of each of these steps in each of two cases. Case 1 on the left here, being that the victim has not visited ashleymadison.com. And case 2, the victim actually has visited ashleymadison. I'll be showing you visuals here for explanatory purposes, but know that in practice, the real attack is invisible to the victim. Now, first, focusing on case 1, where the victim has not visited ashleymadison. Well, we start off the attack by creating a link element on our web page, which initially points to a dummy URL that we know that the victim has not actually visited. And we also add in a little CSS so that our link's background image will be painted by a paintlet script that we've installed into the page. And when the victim visits that web page that we've just put together, the browser will do an initial paint of that link element, coloring it blue to start, as its visited status bit is initially false. And also, as part of painting that link, the browser key will call into our paintlet script to generate its background image of the link that we've set. And after that whole paint cycle runs to the page, we will have a background script embedded on the page to switch the link's destination URL from that known unvisited dummy URL to our target URL of interest, in this case, ashleymadison.com. Now, here in this timeline, our victim has not visited ashleymadison. So the visited property of the link element remains false, as it was for the dummy URL. But in the case where ashleymadison.com does actually appear in our victim's browsing history, then the browser ends up reacting a bit differently to the same set of steps. Starting from the top, again, we create that link element pointing to an unvisited dummy URL. We make sure to set its background image to be painted by our paintlet. And again, the victim's browser does the initial paint of the link element, coloring it blue because its visited bit is false. And again, as part of painting the link, the browser has to call into our paintlet script to generate its background image. And then after the browser finishes that whole paint cycle for the page, our background script, once again, switches the link's destination from that unvisited dummy URL to our target URL. Now, we've done the same set of steps here, but in this case, our victim has actually visited ashleymadison. So that secret visited status bit of the link element changes from false to true when we change out its destination URL. And this secret visit bit is a property which affects the link's appearance, in this case its color. So the victim's browser comes along and sets the invalid flag on our link element. And when the browser renders the next frame of the page, the victim screen, it will see that our link element's been marked as invalid, and so it will repaint it to be purple to match its new visit status to true. But also, importantly, because it's doing this extra paint of our link element, it will also have to call into our paintlet script again to generate that link's background image. So if you line up these two cases side by side, you can see that the victim's browser is committing a big security no-no here. It's branching on the value of this secret visit bit for ashleymadison, such that if that bit is false, it ends up making one call into our paintlet script's paint method, versus if that bit is true, if ashleymadison.com is visited, it makes two calls. So what we've got here is a single set of steps, which, when we run in the victim's browser, this is one of two different sets of behavior based on that value of the secret visited bit for any given URL we choose. And using the CSS Paint API and that link element, we are tricking the browser here into leaking ashleymadison's visit bit into our paintlet script. Then the next step for us will be to exfiltrate that bit out of the paintlet script to wherever we want it to go at the end of our attack. And we actually run into a bit of a roadblock here, because that we do have this browser making this nice, clear, extra call into our paint method. Well, this runs inside our paintlet script. And now say we want to then transmit that information to a remote data collection server we control for blackmailing purposes or whatever. Well, unfortunately for us as an attacker, these paintlet scripts run inside a sort of sandbox, a restricted lockdown execution environment, which is separated from other scripts on the same page. So as it turns out, our paintlet will not be able to make that network request to our server on its own. And furthermore, it can't call into other normal scripts on the same page, and other scripts aren't allowed to read back the pixelated draws. So then it almost looks like this is the end of our story here. I mean, the browser has leaked that visited bit into our paintlet script, but now it's just kind of trapped there inside our paintlet script by all these isolation mechanisms. Well, fortunately, or unfortunately, depending on your perspective, this ends up being yet another case of an isolation mechanism breaking down because it fails to protect against side channels. See, these paintless scripts, despite all that sort of sandboxing, they actually run synchronously with respect to other non-paintless scripts on the page. They all share a single event loop. And so we edit our paintless script, scraping out all that chessboard drawing junk, and we just drop in a call to sleep, which hangs our event loop for a bit. And that will delay the execution of our main script while our paintless script is running. And then the main script observes this delay and informs our remote server that this victim did, in fact, visit Ashley Madison. So by this point, we've put a proof of concept together that covers the whole process for a single URL. Using the CSS Paint API and visited links, you get the victim's browser to act differently based on whether or not the victim has visited a URL we choose, like ashleymadison.com. This links that URL's visit status into our paintless script, and from there we use a timing attack to exfiltrate it out wherever we want to send it. Now, to make this attack really scary, to get a nice high bandwidth number, we're going to have to do a bit more work here. See, we're using a timing attack here, and timing attacks tend to be kind of slow. By their nature, we're injecting a delay into our attack process. But also in this case, we're hanging the event loop, and that ends up locking us down to just running our attack only on one link element at a time. And a single link element can be repainted a maximum of 60 times per second, matching the target frame rate of modern web browsers. And so this caps the attack bandwidth at 60 URLs per second if we're just using the one link element, which is a far cry from that 3,000 to 6,000 number we quoted up top. So what we'd like to be able to do here to get around this is to put a ton of link elements on the page at once, and have the browser repaint them all in a single frame. But unfortunately, this is infeasible as long as we're still using a timing channel. Now, we're dealing with browsers here, though, and browsers are incredibly complex beasts. So the odds are really in our favor here that we'll be able to find some other covert channel in the CSS Paint API. And in fact, we did here in the form of this weird, unintentional behavior with the register paint function. This register paint is a function which can be called from inside the paintless sandbox. We found that we can abuse it to control the width of a specially structured element on the outside of that paintlet sort of sandbox. We start off by first creating one of these weird special elements with the code we're showing here. It uses what's called a CSS pseudo-element selector in conjunction with the CSS Paint API. And so we have our attack's main script inject one of these weird things into the page. Then from inside our paintlet script, we call that register paint function at a certain point in our browser's rendering cycle. And it turns out that if we make this call at the right time, then that weird element outside of the paintlet script will end up getting a relatively large width value, like under 54 pixels. Versus if we don't make that call to register paint from inside the paintlet script, then we'll end up getting a small width value, like 4 pixels. And once again, I'm showing you visuals here, just for explanatory purposes. In practice, this is all invisible to the victim. So to apply this back out to our history sniffing attack, when our paintlet script detects a link is visited, then it makes that call to register paint, which in turn causes one of these weird elements in the page to end up with a big width value. Versus if our paintlet doesn't detect the link is visited, then it doesn't end up making that call to register paint, and so our element ends up defaulting to that small width value. Finally, to complete the exfiltration chain, then for our main non-paintlet script, we measure the width of that element by simply calling the getBoundingClientRect function, which gives us the dimensions that the element appears as on the screen. So with this in our toolbox, we can now rebuild our attack into a new amplified high bandwidth version by running our attack over a ton of link elements at the same time and applying other similar tricks. And the results of this work can be seen in this demo, which I'll switch over to now. So what our attack is doing here is it's taking that top 100,000 sites provided by Alexa Internet, and it's just scanning through all these URLs, plugging each one of them into an invisible link element, one of many, which has been injected into this web page. And it's doing that scan at around 6,000 URLs per second, and it will complete after around 17 seconds. And after just a little bit of post-processing and the exfiltration of bits from the paintless scripts, then you'll see this nice list of websites which this victim has visited. So we've gone through and we've ticked off all the boxes for the CSS Paint API-based attack. We went from identifying a feature that seemed potentially vulnerable to being used for history sniffing, which produced different sets of browser behavior on a secret visited bit, depending on the secret visited bit of the URL. And from that, we were able to build up a real-world high-bandwidth attack. But now this isn't the only attack that we present in the paper. If you recall from the top of the talk, we actually came up with 4 new history sniffing attacks, each exploiting a different feature of the modern web platform. So I'll flip through the remaining 3 briefly, just to give you a sense of each of them. And for each, I'm going to mainly highlight the differences between the visited and unvisited cases for any given URL. In the first, we set up a situation which results in a measurably slower paint performance for the visited case relative to the unvisited case. We accomplish this by applying some complicated CSS effects involving 3D transforms, which are a thing now, to a link element. And then we do that same toggling trick in its destination URL, but many, many times in a loop instead of just once. The second targets SVG fill coloring. It uses a similar setup, but which intentionally drags down paint performance in the case where the target URL is visited. And it mixes a really complicated SVG image with lots of overlapping paths, like the one on the top right there, with some CSS rules to accomplish that. And the last one, unlike the rest, we're not using the visited links feature, but instead we perform a cache timing attack on the new JavaScript bytecode cache mechanism added to Chrome. We take a script embedded in our target page, and if that user's browser is compiled it before, because the user visited that target page, then we get a very fast load of the script thanks to the bytecode cache, versus a slow one without it. And we're able to make this cache timing attack particularly reliable by applying some tricks to really zero in on the compilation step for the script and get a very precise measurement of just that step. So now, why do these attacks matter? Well, I say it's scary we were still able to put them all together 16 years on from the original visited links disclosure. It means that browsers still don't have robust structural protections they need to properly safeguard the history data from attackers. And what sort of attackers would those be? Who are we dealing with here? Well, if you look at that 8-year period between when the original history sniffing attack was disclosed and when it finally got patched, according to studies at the time, actually some of the top websites in the world were using history sniffing attacks to actively profile their visitors. And this was so widespread that there were actually SaaS options for it. You had internet marketing firms popping up, pocketing their commercial, prepackaged history sniffing solutions, positioning them as analytics tools with pitches like, track which sites your customers visit, learn if they've been looking at your competitors, and our patent-pending technology gives you insights into your visitors. And that second one with the patent, Telium, boasted big clients like Hasbro, Nokia, Best Buy, DreamWorks. So all these major companies were systematically violating their users' privacy in production and at an industrial scale. We really can't let that happen again, which is why we're proposing a structural fix, which goes to the root of the history sniffing problem, ending this chase to plug up leaks to the surface level. Our defense centers on this concept we're introducing, building on previous work called refer origin labels. At a high level, if the user visits a page at a.com, which contains a link pointing to a page at b.com, then if the user clicks on that link, S3 entry is created for the b.com page, and that a.com link turns purple thanks to visited links. Under our scheme, that b.com history entry will be labeled with the origin of the referring page, in this case a.com. But now say the user navigates to a different page at c.com, which also contains a link pointing to that same b.com URL. Under our mitigation, that c.com link will be colored blue instead of purple. The browser hides from c.com the presence of history entries not labeled with a matching origin, giving up a little bit of functionality for the sake of cutting off history leaks at the source. Now from here, if the user were to click on that c.com link, then conceptually the browser would create a new history entry for that b.com URL, but this time labeled with the referring origin c.com. So when the browser goes to draw a link and picks out either blue for unvisited or purple for visited, then this lookup ends up involving a lot of different components in the browser stack. Here we have web content from c.com causing the renderer to talk to an IPC layer to then ask a storage engine whether or not this c.com URL was visited. And our goal with this mitigation in the end is to blind c.com pages from the presence of history entries not labeled with a matching origin. One possible strategy would be to implement this at the web content layer itself. But to make this really robust against, say, side channel attacks like the ones we presented here, it would be best to apply this blinding to every component we can in the chain. And we would tag all of the messages that they're exchanging with the origin on whose behalf this lookup operation is being performed. And 2 last points about our defense here. First, we'd like for it to be applied not only to history data, but also cache data. This would turn into the whole other saga of cache timing against attacks against web privacy, like the one we showed with the JavaScript bytecode cache. And finally, this new approach could entirely replace all the previous ad hoc mitigations that browsers have applied to past history sniffing attacks. As one W3C member put it after reading our paper, we could scrape out all the duct tape, making a mess out of so many browser features by just turning off the wire of the faucet instead. To wrap up, we present 4 new history sniffing attacks, each targeting different modern browser features, which allow an attacker to invisibly test whether you visited exact URLs at high bandwidth. Our most powerful attack runs at 6,000 URLs per second. Instead of expanding the tangle of duct tape, which browsers have layered on to patch up history sniffing attacks so far, we propose cutting them off at the root with a refer origin label mechanism. Now, here I'll be happy to take any questions about our attacks or proposed defense or whatever.
Thank you for the talk. Very interesting. Are there any questions? Then I ask a few questions. First of all, the visited link property is still necessary today. Today in the web, we mostly click on logos or something if we visit websites.
So one case where it's very visible is, say, a site like Reddit, for example, where you have that constant stream of links. When you click on one of those, you want to be able to then, when you come back to Reddit, see that, oh, I've been to this post before, I'm not going to waste time clicking on it again. So that's the main use case is still here.
Good question now.
Thank you for an excellent talk. I have 2 questions for you. The first one is, do you have concept code online?
Oh, proof of concept. So we are going to publish. So the question was, do we have our proof of concept published online? And we're going to do that after this talk is over.
Okay, cool. Second, the side channel you mentioned, loading an external script and timing. This does not exactly correlate 100% to history, right? I mean,
yes.
It could be just thrown away, but the site could still be in the browser history.
Okay. Yeah. So first off, the question was that whether or not the script is in the cache doesn't exactly correlate to history, and also it can be thrown away sometimes while the history entry still maintains. So these history entries actually are these cache entries are actually persistent to disk and survive for quite a long time, including like past full reboots of the system. And then if you pick a script, which is say, the granularity of this attack is lower than say for exact URLs. But if you pick your scripts cleverly, like for example, if you pick one that is only loaded for a members area of a website versus just their homepage, then you can get some very clever information out of it.
Okay, thank you very much.
Very clever tricks and a great presentation. About your suggested defense, it's not semantically equivalent to what we have right now, right? Because you will only show that a link was visited if you are on the same page as from which you have visited the link. Do you think that users will accept this? Because that's really different from what it is right now.
Right, so the question is that our proposed mitigation is not exactly equivalent to the current functionality. I think, obviously we can say you might follow up by running user studies or something to see how people respond. But I think our mitigation still covers the most visible use case, which I mentioned before, which is like a Reddit page where you have certain URLs that you want to see which ones that you've clicked on from Reddit before. And so that will still all work. The only thing we'll break is if you had visited another page from some other website, and then you go to Reddit and it doesn't show up as purple from Reddit. But I think that's we can see if we study this. But I think overall it's a very small cost to pay versus finally plugging up all these constantly springing up history leaks.
Thanks.
Okay, thank you for the presentation as well. So I have also a question on your defense. So there are policies which allow you to restrict the usage of referrers, and so that they are removed or they are not used because of privacy reasons. And your countermeasures are using referrers to actually apply these defenses. So can you comment on this? So how about the countermeasures, these policies which restrict the usage of referrers, and how to also behave them?
Right, okay. So when I say refer, I don't necessarily mean to tie this to the actual refer header, or the same concept of which page you click on to get to the other page. You could tie this to disabling our refer header also disables visit link say. You could make that decision. That's really a judgment call for browsers to make based on what they think is best for their users.
In the presence of caching proxies, or if you have like any shared cache between users.
That's a very excellent question, and it's not something we really investigated in this paper, but I think there is actually a large body of work around cache timing attacks on the web, so I'm sure there's an existing study on that out there somewhere, but it's not covered in our exact work.
So just a follow-on question with your proposed fix. What kind of overhead do you expect that to impose upon web browsers?
So the question is, what kind of overhead do we expect our proposed fix to impose on web browsers? I would imagine it would impose a very small overhead generally, because we are simply adding another field to each of these existing history entries. We already have these database systems that are being searched to come up with these answers to history queries. And adding one more index that lookup probably won't impose too much of an overhead. If you apply them to cache entries, then the overhead is maybe a bit more because it causes, say, the first script load for a page to go through the full compilation step instead of using the cache which is generated for another site. But that will only happen for like the first time that the page is loaded, and all other loads will subsequently be optimized. And since Chrome is the only browser which actually implements bytecode caching, having most of bytecode caching versus having, it's still better than having no bytecode caching. And even having no bytecode caching seems to be alright for the other browsers, which don't have any.
With that, I think we should thank the speaker again.